Okay, everyone, welcome to today's version of the Inverse Problem Seminar. So we are very happy to have Lars Ruthotto here today, which is an expert on computational methods, both for inverse problems and machine learning. And today he will be talking about differential equations for continuous time deep learning. So thanks a lot, Lars, for giving a talk in our seminar series.
Yeah, sure. Thank you, Knut, for having me. And also thanks to Katja, who will hopefully join later, because she did also some magic behind the scenes to get everything scheduled up. And yeah, welcome to all of you here for my talk. I did warn Knut, so I kind of we're going to break the rules or change the rules a little bit in this Zoom. So if you want to, you are welcome to show your video also. I have a screen where I could see people. But no pressure, and bandwidth, of course, could be an issue. But anyway, I'm trying to do these things as interactive as possible, especially because I feel with this topic, I may be a little bit of an outlier in the seminar. I mean, I've watched through the excellent YouTube channel and it's been a while since I give an inverse problems talk, so I welcome any questions. I don't want to lose anyone, but I also want to give you some of the recent, like a taste of some of the recent work that we've been doing by maybe bringing some of the inverse problems ideas to deep learning and the other way around. Okay, so let's jump into this. I basically want to, in the first part of the talk, explain to you what do I mean by continuous time deep learning. And I'm going to introduce that in a simplified setting, which is called the supervised learning problem. So where you know your inputs, you won't know your outputs. You basically want to find a function approximator between the two. So think about you have some training data that is given by these red and blue dots, and then you want to learn the underlying function that assigns colors based on XY location. Okay. So you have some features, you have some labels, you have some minimization problem. We have a regularizer like we're supposed to in inverse problems or learning problems. And then what I'm going to show you is how to build the F so that it is a continuous time model. And these are now known under neural ODE and other things. This part of the work is sort of the beginning of a sort of little survey paper I wrote for AMS Notices, and that's about to appear. So I have it linked here if you're curious. And then after understanding the supervised learning, understanding what continuous time deep neural networks look like and how to work with them, I want to go to a very useful application also to this audience, and that is generative modeling. And these days and age, so we've been working on generative modeling for a couple of years now, but since like a year or so ago, or a year and a half, I need to explain really what I mean by generative model. So you will not learn about ChatGPT and LLMs and text generation, because those actually use a very different mathematical setting. But what I'm really interested in this part of the talk is learning complex high-dimensional distributions. So you are typically given some samples, x1 through whatever, from some unknown density. I'll denote it as rho x. You see these blue dots up here. These are your samples. And then what you want is you want to be able to either generate more data that looks like your training data, or you want to ask questions like, what is the density of a given data point? And the goal here is you want to do a coordinate change. So you have a distribution rho z. Let's see, this is the density of a Gaussian in the bottom here. And then you basically want to apply a change of variables to define the likelihood of a sample, and then find the coordinate change that maximizes the likelihood of your samples. That's a very short version. We'll go much more into depth later. Turns out that if you model this F with a continuous time network, you actually get close to the state-of-the-art models. If you add some noise, you are at what's called a diffusion model. So if you think about image generation, what I'm going to show you is sort of a baby version of image generation methods that you could build with the addition of being noise. But those networks, so image generation is a continuous in time deep learning problem. Text generation, not so much. So we'll talk about that more. And then I'm actually going to show you something that may be useful for inverse problems with people. You could also change the rules a little bit, and you could ask yourself, can I learn a conditional distribution? And the answer will be yes. And that, of course, will be very useful because you may want to have a distribution for your model parameters given some observations. So that's how we're going to dive a little bit. So I've been trying to gear this as much as possible to inverse problems and showing you some of the potential that I think is still there to be explored. So short agenda. Intro to continuous and time deep learning. Then we'll talk about generative models, and we'll talk about basically three things. So one is called a continuous normalizing flow, then an application to simulation-based inference. So this is like an inverse problems application. And then some notes on score-based diffusion models that also build up on some of the things that my PhD advisor a month ago in the seminar, Martin Burger, kind of mentioned that, these models, like, it's not so clear how they work actually in function spaces. And I want to kind of at least give you a taste of some techniques how to put them in function spaces. If time permits, we can also talk about optimal control. This may not be the perfect audience for it, but there are some underlying mathematical things or underlying underpinnings that we can carry over. So the main works that we're going to chat about are these ones here. Okay, let's dive right into it. And as I said in the beginning, this is supposed to be interactive, so you can ask me anything, anytime. So continuous time deep learning. Hopefully this will not be too repetitive. You've seen maybe some of these things. So we have some training data. We have some deep neural network. In this case, it has two inputs because you have X, Y coordinates. You have one output that's red or blue. And then sort of once you've kind of learned and trained the weights of all of this of this DNN, you get some classification result. And then you are happy because the red dots are in the red zone and the blue dots are in the blue zone. Okay, so how do you do that actually? Here is a bit more mathematical setting, and I'm going to use a specific type of neural network called the residual neural network. So the way that goes is you take your input, let's call y, is a vector of R2, you embed that with some linear transformation into some other space, and then you have quite repetitive layers where the first layer here kind of the stuff that is learned is this part here that is sort of the update, the residual between U1 and U0. This is a break of change in neural networks. So before the residual neural network came about in 2016, you didn't have this first part here. And that meant like you had a multi-layer perceptron architecture, and they've been around for many decades. But they are notoriously difficult to train when they become deep because they have a hard time, for example, just learning to do nothing to basically represent the identity function. So this addition makes this super easy because then if you add a layer and initialize those weights with 0, then nothing happens and you'll be good. I took the liberty to add a little constant h here that we will kind of denote as like a step size, because once you take a look at this for a second, then it rings some bells in terms of ODEs and so on. So the original paper had h equal to 1, but if you want to relate this to forward Euler methods, then you would want to have an h here. Then you can have any activation function you like and so on. And in the end, you lump all of these k's and b's into a long vector called theta, and that's your model. So the output of the last layer is going to be your model output. And then you train those weights by solving a minimization problem. So you have some loss function, and in this example, cross entropy, with maybe some regularizers. So it's a Tikhonov regularizer. Machine learning is called weight decay for some reason. And then you go. It's a stochastic, high-dimensional problem in general. So you have Monte Carlo integration and so on. The nice thing when you work with these ResNets, you can actually look at what they do to the feature space. So everything up until the last layer is sort of related to kind of a feature transformation that makes the data nicely separable. So here is the trained network. The frames of the video are the different layers. And what you can see here is that toward the end of the video, see if I can actually stop this, it makes the blue points be on one side and the red points on the other side of a hyperplane, which is the weights of the last layer. So you have some interpretations of what's actually going on in this network. So see, this is like the end of the video. Hope I can stop it. See, yeah, maybe not. But you could see that at that point, everything becomes linearly separable, and then stuff works out. So that's sort of was a groundbreaking paper in 2016 in computer vision, doing image classification better than anything else, having hundreds of layers and still being able to train these. The benefits of this type of architecture are actually by now probably quite well known, but let's go over them. So you could relate this to a forward Euler approximation of an initial value problem where you are learning the dynamics and they are nonlinear, non-stationary. With certain choices, you can mimic the ResNet. You can have results, or some people have shown results that the training becomes easier because the loss landscape becomes nicer. So this is a comparison of so it's a very high-dimensional visualization that they kind of did in this paper in a very sophisticated way, where they kind of wanted to see what is the benefit of having this, what they call skip connection, or the residual part of the architecture. And if you are an optimizer, you would probably much rather have something smooth like this than something smooth like this around the minimizer to optimize. So there are some of these benefits, and these are like really deep networks, and kind of the residual connection here was really important. They are still, I think, among the state of the art. So you see some of these components also in transformers and some more modern architectures. Benefits are they're easy to train and add depth to them. Few people here in the audience actually have done some nice contributions there too. So yeah, you can ask questions here. For example, what would you do in terms of how do you design this layer, this F? Because remind you, this is not like a physics application where this is given. Basically, as long as you can get the job done and get results, anything goes. I want to note that some of these ideas have actually been around pre-ResNet. So in hindsight, when you look at some of these papers, they actually look almost like these ODE or ResNet type architectures, and they're quite interesting actually to look at because they show some benefits quite early on in a previous wave of deep learning. And that's maybe one of the things. I mean, deep learning, of course, is this very fast-paced, moving field. And people sometimes forget that there have been AI summers before, and some of these ideas actually become repeated every now and then. But definitely, I think the difference now is that we have much better tools to actually work with these networks. So they become quite popular. A very early work we've done here was actually to ask a very simple question, because you could think about this as an inverse problem where you want to learn the weights given some observations, like some labels. And one of the first things we would want for an inverse problem is that the forward problem is stable, right? So if you have small perturbations to the inputs, you would want to have small perturbations to the output. Turns out, of course, that not all ODEs are stable. You need to do something. And we've explored a few things. I think Ferdia, who's here, he has done also quite some nice work on bringing some of these things to the discrete level. So it turns out that if you design this F in certain ways, so you could be inspired by Hamiltonian networks or antisymmetric networks, and then you pick an appropriate discretization, for example, symplectic integrators, you can basically go to the continuous world, discretize the whole thing, and come back to something that is different from where you came from, and I would argue better than the ResNet. So ResNet is a forward Euler discretization of an ODE that may not be stable, but if you kind of model the continuous system in a stable way and use symplectic integration, for example, you can actually end up with forward-backward stable discrete networks, and they have advantages in terms of memory and other things. So surprisingly, sometimes you don't sacrifice performance when you do that in terms of how well you can train these networks, and you do gain computationally sometimes. There have been many approaches since, and this really needs updating constantly, so you can have more expressive architectures. People have used ideas called multi-level training, because now, and I should highlight again that the continuous in time. Hopefully you saw that. So the ODE, of course, has a time component. So that's the continuity. The time is artificial. but you could roughly think about it as relating to the layer or the depth of the network. So rather than having a discrete number of layers that goes from the original data to the transformed data, you now have like a continuous slider that you can use. So you could do multi-level training. So have coarser or fewer layers, and then initialize finer layers. You can go more on the theory side, kind of see what are the best results in terms of making these networks stable forward, but also backward stability is important. I'll touch on that in a little bit. You can look at convergence and optimality conditions in continuous space. And many things have been done based on these ideas and are still being done. And there's still an interesting area of research to kind of see how can we bring a little bit more mathematical interpretation into this area. A big player in this game is this work called neural ODEs. So maybe some of your students have been asking you in an ODE class, should I take the class? And then the answer is yes, because then you can understand this great work. We've got a lot of traction. So it's a paper that popularized these ideas in the machine learning community. Had some bold claims. Some of them have been debunked, but a couple of nice things have really survived. So in some sense, in machine learning audiences, I always need to tell people, so the paper here claims that you can get rid of all the memory. I mean, people who work on time-dependent inverse problems know this probably. So when you compute a gradient, because you want to kind of do a map estimation or whatever, you basically need to solve an adjoint equation, and the adjoint equation takes up a lot of memory, right? So people in inverse problems know this in and out. The proposal here was to just integrate the ODE backward in time, which of course is a terrible idea if you're working on the heat equation. And this was then also noted by some papers and illustrated that it's not always a good idea. You need to do some extra work. So people who work on FWI or Helmholtz type equations, they are allowed to kind of integrate backward in time. But of course, not everyone is. But a nice thing is that this paper actually gave new uses to these architectures, because in supervised learning, they may not be the most effective architectures in most cases that we're seeing. Especially now they've been replaced by other things called implicit networks, for example. But in generative modeling, this was, I think, one of the first paper that kind of explored the use there. I'm going to show you kind of how you can use these techniques. Yeah. In any case, sort of, you can now think about the problem in continuous time. So if you have a supervised learning problem, then rather than having this messy forward propagation with a discrete number of layers, you could think about this as a control problem, or as an inverse problem with like that is dynamic, where you want to learn network parameters based on some inputs and output observations of your model. You can actually, of course, eliminate this concern because it's an initial value problem. But what I wanted to show you also is that you can kind of think about this at a PDE level. So here is an attempt to explain why this is actually a PDE constraint problem, which conceptually has led to some insights and some nice works. So you could think about a function u, which is a scalar function that is like this labeling function. So it's now time dependent. And let's say at the initial time, it's just a function that is affine in the input to in the features. So this sort of, if you want to look at this here, so here, this background, this is like this affine function, and then sort of flattened out, which is the typical thing in deep learning, which the softmax kind of transformation or logistic function would do for you. So you can then think about this as a PDE constraint problem governed by an optical flow constraint, if you will, or just a transport equation, where the property here is, of course, that a point can move along characteristic curves, which are precisely given by this by the dynamics with f. So f is the velocity, and they don't change the intensity. So that's a property, right? It's a characteristic solution. So in some sense, you can think about the supervised deep learning problem as minimizing a objective function, a loss and a regularizer, over a high-dimensional transport equation. Okay. And the twist here is that the initial condition is not given precisely, because you can still also learn this W and the mu. So you don't have a fixed initial condition. But I mean, potentially, I mean, actually one thing I told Knut, so this summer we are running an RU program, and I have in my previous life, I worked on a problem called image registration, which is actually trying to solve these type of problems for images. And we're kind of looking into creating new relations now between neural ODEs and the image registration problem. Or the other way around, I mean, the image registration sort of is a low-dimensional test case of these high-dimensional machine learning problems. But of course, I should always say that here for illustration, I'm going to show you 2D examples, but the real meat is, of course, in spaces of images, so conceptually infinite dimensional. Okay, so this is continuous time learning. So you kind of have a specific type of architectures that have an artificial time to propagate the features. So how can we use that beyond the supervised setting? So in the supervised setting, again, you match input points to output points. In generative modeling, you map distributions. So here's how that typically goes. So a continuous normalizing flow looks potentially quite similar to the supervised setting, but it's very different in spirit. So you have samples. In this case, you only have vectors in RD. You don't have labels. So it's technically an unsupervised problem. But you could think about it as supervised on the distributional level. So you have these points, and then you want to learn a coordinate change to a simple distribution. So in my characterization here, we're actually going to 1D now. So you have some points, these blue dots. You have a simple distribution, your 1D Gaussian, and you want to construct a coordinate change. And also an idea that's been around like in image registration and other like differential geometry areas, and this in low dimensions, is to construct this coordinate change as the flow of a differential, as a flow of an ODE. So in this case, you take your data point, your x, as an initial condition. Let's call it z at time 0. You set to this xk, and then sort of you follow the velocity like a characteristic curve, and then once you have done that, let's show you one. So you have your blue dot here, you follow this characteristic curve, and then you map it to the Gaussian, and then with the change of variables formula, you can figure out what is the density that you assign. Of course, when you do this, you need to track what the point is doing, but also you need to track the density changes locally. And the nice thing, so when you start out, you have this determinant of the Jacobian, which may sound very scary because this will be a high-dimensional problem, like in 100D or 1000D. But the nice thing is when you go to the log density and you define the coordinate change through this ODE, the log determinant is just given by the integral of the trace of the Jacobian of the velocity. So this is a nice simplification because that way, so the velocity is then going to be represented by a neural network. If you could compute the Jacobian and the trace of that, then you just integrate this within your ODE solve. So you initialize this with 0, and then you integrate it. And this is coming out of this neural ODE as a follow-up for the neural ODE work. And it's been quite a substantial contribution to this generative modeling area. It's still being used. And once you've done it, you can actually have a density estimate too. So there's like a density estimate for your data X. Of course, one of the things that's missing is a sense of what do we look at in inverse problems? We want existence and uniqueness ideally. So I mean, sure, there exist mappings between any reasonable distribution and a Gaussian. But in this problem formulation, and I try to make a cartoon version of this here, is basically any flow that has the same beginning and end points will give you the same density. And this flow may not be one that is super nice to integrate because it kind of takes some curves and some twists, and things get close and not so close. So Didn't take people very long to figure out that maybe you want to force uniqueness into this, and also kind of get simplicity in by looking at, for example, transport costs. Because you could interpret this problem also as like a transport problem it's like semi-discrete, because you have you're not mapping a density to a density, but you're mapping samples to a density. So here's one of the ideas, and to just show you what happens, and I'm going to get you the mathematical underpinnings in the next slide. Is the one simple idea is let's basically add some transport costs to the whole game. So without looking at transport costs, you got transformations like so. But if you, and now a lot of new players here, so let's go through them. So CL is kind of, but I did already one change. So I represented the velocity as the gradient of a scalar function. Okay, for now, maybe it comes out of nowhere, but I'll argue that this is actually a reasonable choice. And then the CL is sort of measuring kind of the displacement and integrating that. So that's a measure of cost. Like you would prefer to have, if you want to have shorter curves, then you would want to minimize this cost, right? And then the CH, that comes out of nowhere for now for people, but I'll make a sense of this next slide. So what happens though when you kind of not just look at what is the maximum, what is the density, and what is the maximum likelihood kind of your samples, is you get straight lines. And straight lines, so still the same mapping, is you can fit the same fidelity, and you have the same kind of approximation theory results, but what you gain is you have very simple characteristics here, ideally straight lines, which computationally, of course, you can now take advantage of, and there are many works on kind of these ideas here. Okay, so where does the phi come from, and so on. I want to show you just some background. You could interpret the whole thing into a bigger class of problems called mean field games. So on a PDE level, basically the maximum likelihood training problem with transport cost as regularizer looks like so. So this is the maximum likelihood term. You have a PDE constraint. This time it's a continuity equation. So it's not intensity preservation, but it's mass preservation. You start basically with the latent distribution with your Gaussian, and you find out what is the velocity, so that at the terminal time, and again, it's Benham-Rupert-Nier type, like dynamical OT with artificial time, that maximum likelihood gets maximized, and you have some transport cost penalty, the usual stuff. For this type of problem, you have a maximum principle that tells you that the velocity is a negative gradient of a potential or value function, depending on how you want to look at it, and that this one satisfies a PDE also. So this PDE system, actually, Lars and Lars have proven that this is actually necessary and sufficient for these type of problems. There are two problems, maybe, or three. So one is, of course, there's a forward-backward structure. So this PDE here goes forward in time. This one goes backward in time. They live in very high-dimensional spaces. That's another issue. And actually here, for the generative modeling application, we cannot write down the terminal condition for the value function because we don't have access to the density rho x. We get away with it in the loss function because here we can just sample because it's an expected value. So that's sort of the nice thing here. But still, this viewpoint gives you a lot of structure to play with. So you can now basically, to go a little bit, get some insights into the learning. Of course, the continuity equation has characteristics, and the density along the characteristics, or the log density, is actually described really by the flow of the gradient and the Laplacian. And the characteristics of method of characteristics, of course, is scalable to high dimensions because you don't need to have a mesh to solve the continuity equation. It's nothing you can do. And all of these other things, once phi becomes a neural network, a scalar valued neural network, become actually tractable to compute. So that is exactly what people are doing in this field, and we're also doing. So you model this value function as a neural network that has a scalar output. You can use your favorite way of doing this. We use residual networks, as I introduced before. And then sort of you need gradients and you need Laplacians. So that may be a little bit tricky because gradients are easy. Automatic differentiation has really matured over the last years. Everyone has it now. But Laplacians are a little bit challenging because you, in some sense, are limited to matrix vector products in automatic differentiation, and those go forward and backward. So in our codes, we usually just compute this by hand, because then you can kind of simplify things and making them really fast on GPUs. And you can map interesting densities. So here are some of the benchmark examples, conceptually simple problems, but actually when you think about them, they're challenging in some ways. So basically, these are data distributions and histograms of those. I can see they are a little bit noisy. So it's not a denoising problem here. What really needs to happen here is that you map these samples to a Gaussian, and then that implies the image in the bottom here. That's a density plot. And I'm just waiting for people to wake up and unmute themselves and scream into that. How can you do this? Because aren't you using a diffeomorphic mapping, and aren't these samples sort of always like disjoint, and like how the hell is this going to work? And of course, the thing here is that you are regularizing by limiting yourself to diffeomorphisms. And that's maybe also one of the issues with continuous normalizing flows, is that they are based on a diffeomorphism assumption. So you cannot use them to kind of get the complete classification or complete high fidelity. So you see that here, maybe that there is always some little mass that is lost in space someplace, because that's one of the assumptions that you're dealing with. But they have been quite powerful for many applications. And I will say that I promised to say something about diffusion models. You could think about the diffusion model as adding some Gaussian noise here, so turning this into an SDE. Of course, many other things need to happen then in terms of the training. That's why I'm not going to talk about it too much. But yeah, so this is like a couple of things. You can scale this to high dimensions. That's the main selling point, because in 2 dimensions, I would honestly just use a Benamou-Brenier type solver. But we did make some interesting comparisons at some points on mean field games to solve them in 2D with Benamou-Brenier ideas, with finite volumes and good discretizations and Newton type methods. Put that side by side with a neural network that you train almost with eyes closed, and stochastic approximation schemes and just some linear algebra, and they perform actually quite well. So educationally, that kind of made us think a little bit about what we actually want to now kind of recommend people do. Talking a little bit about using these things for inverse problems. So let's say now we want to learn a posterior distribution, which should be interesting for people. You see here a comic or cartoon on the right, where basically we now train an ensemble of these models. So you want to sort of sample X given Y. In this case, it's like a 2-dimensional data set. So we have samples from the joint distribution in blue. And then for every fixed Y, sort of you want to learn how to map a 1D Gaussian and adapt it to the data points. If you have that, then I can draw samples from the conditional distribution, which in general is difficult. If I only have samples from the joint, it's usually difficult to come up with samples from, or densities from the conditional. So this is sort of the crux of it, and you see here is like illustrated for 3 different Ys. Every time 0, all of these models start with a 1D Gaussian, and then they adapt to the samples. So how do we do this mathematically then? If you've been following along, the change actually is quite simple. You start out with samples xy from the joint distribution. Let's say X is the parameter of interest and Y are indirect noisy measurements, which is the inverse problem setting. then you pick a reference distribution in Rn, so in the X space, sorry, and you train an invertible generator. Basically, do a coordinate change from the X space to the Z space, to the latent distribution. Use a change of variables, and you're done. And now everything just gets another argument. So this transformation here, so I call it now the generator G, depends not only on X, but also on Y. But if you compute the Jacobian and the determinant of the Jacobian, then this will only be in the first argument. So you could think about it in many ways. One is to think about amortization. So you amortize these generative models for all the different Ys. That's maybe one good way to think about it. And I mean, you do see that the difference in Ys really gives you different flows or different generators. And that has to be the property. Of course, we'll define G as a neural ODE, a continuous in time model, because that way sort of we can think about this again as a mean field game. In this case, it's actually a parameterized family of mean field games, because for every different Y, we have a different dynamics and different optimality conditions. But more or less the same techniques apply. We were motivated here by an application in simulation-based inference. So these are techniques that basically try to solve Bayesian inverse problems outside of the traditional Bayesian setting. So think about you have a problem where you have an intractable likelihood, or you have an unknown likelihood. So these are completely based, you can simulate data from the joint distribution, but you don't necessarily can write down in a clean fashion what is the likelihood, what is the prior, and how does the posterior actually look like. So in these cases, the goal is to sort of bypass the modeling and learn the conditional distribution directly. So this makes this, if it works, it makes it widely applicable, because as long as I can simulate the data from the joint distribution, I'm good, not limited by tractability. And it could be computationally efficient. And that is one thing I want to hopefully explain and convince you a little bit of. Yeah, this we're going to skip. So everything gets parameterized. We're good. But I want to kind of show this side by side on a test problem. And I should say that you can find all the details in this paper, which was actually written by one of our undergrad honor students here last year at Emory. So Oliver Wang, he is now actually at Yusuf Marzouk's lab. So this kind of was really nice work. And it's on archive and submitted hopefully pretty soon. But one thing that we're trying to look at is a inverse problem. This is a simple problem, or like low-dimensional problem, where you have stochastic predator-prey models. You have two populations with two parameters. So you have a variable in R4 that you want to infer. And the whole thing is governed by an SDE, which makes it a bit more challenging in the Bayesian setting. You run your SDE, you get 9 summary statistics. And based on this measurement, you want to tell what is the X, the underlying X. The best thing people could come up with before using deep learning methods was sequential Monte Carlo. And you see sort of on the right-hand side here is for one particular measurement, for one observation Y, how the posterior looks like, sliced in different directions. So you see, maybe you can see these red dots, like the true solution, and then the mass of the posterior is sort of nicely centered around it. And the posterior gives you a good impression of what is the uncertainty also with respect to the parameters. So sequential Monte Carlo has a few knobs to turn. You need to get some noise level that goes to 0, some smoothing, and so on. And it takes about 6 million, let's say, SDE solves to kind of get a large number of high-quality samples from this posterior. With a generative model, the computation works very differently. So we don't have a sequential data generation. We just in the beginning sample from the joint distribution. So you sample from the prior, you run it through the SDE model, and there you have your XY pairs, right? This can be done in parallel, and you can just stop it at some time. So here we did like 50,000 of these samples. Then, you know, of course, we made the GPU crunch to solve the generative modeling problem. But that's just some GPU time, not so much art involved in this anymore. And here is sort of the samples that you get. So this image should look close to the image on the right. There may be some differences when things are a bit more spread out or so, but it gives you from 50,000 samples, you can already learn quite a lot here. If you throw more samples in, then these become maybe a little bit sharper. So it's like 500,000 samples. So now already you can do the math and you can realize that the computation considerations are very different because you have 10x fewer samples. But I would say you are actually learning even more than you learn from these 6 million samples in MCMC. Because now, if your data changes, so if you picked a different Y, what would you do in MCMC? You would go run your Markov chain again. So we've done this for another one. Takes, I don't know, 18 million samples this time because there are some non-trivial changes that you need to do in convergence criteria. But for these generative models, they are already amortized. So basically, you have no more training. It's like 0 more samples, and you get something that looks approximately close. So that's one of the sort of interesting use cases, I think, in inverse problems for generative models. And this is like just to show you one particular one that is modeled quite cleanly from optimal transport, differential geometry. You can also use diffusion models, I think, for these type of problems. But the whole point is when you want to use sort of machine learning for these inverse problems is I think it's you benefit from modeling this at the distributional level and not in a supervised learning fashion. There are some works that have done this years ago, and I think we're sort of seeing the limitations of that. So that is one use case in inverse problems. Since Martin just joined, I want to show him some work on what to actually do in infinite dimensions, which surprisingly, generative models like image generation is not modeled at. So here's like one project we've been having here on diffusion models. So the way diffusion models work, I think by now you've seen this picture or variations of this picture many times. You get your clean image, like an image of this dog, and you add noise to it through some process. And then sort of what got me confused for quite a while in this business was I was sort of, okay, so once I have added noise to an image, I cannot undo the noise. And this whole thing must be just a hoax. But the problem, or the thing is, again, that, I mean, what me confused is you should not look at this at a point basis, but on a distributional level. So you can add noise to this dog image until you have nothing, no information left. And then you can learn a reversed process that gives you another image, but this may be a different dog. So that's kind of the whole point. So what happens is you have a complex distribution of all the dog images. You map them to a simple distribution of all the Gaussian noise images. And on this distribution level, this is a reversible process. Of course, it's easier said than done. I mean, you're talking about many GPU hours to learn this inverse mapping. One thing that got us interested in this was were two things. So first of all, like when I grew up, like image processing was done on a PDE level. So we're not talking about a pixel grid that represents these images, but we're thinking about, say, functions in L2. If you think about this on this level, then you realize that a few things are, well, there are actually many still interesting questions. So one is sort of the well-posedness. So what happens if you have now infinitely many pixels in some sense? Then you realize that adding Gaussian noise to the images is not well-posed. So you need to have sort of some coupling between the pixels or some spatial information that is kind of happening. So technically, the covariance operator needs to be trace class. So you have decaying singular values in there. But also, I think the score function that you're learning is actually not a score function, it should be a score operator. So in this study, what we've been looking into was, okay, so what happens when we change the noise model, and what happens when we change the operator architecture? And there are quite a few papers that do this in a similar fashion, and I think it's still interesting to kind of see how to make. So one thing ideally I would want to do is I would want to have generalization across resolutions. So I could train on coarse images, have a diffusion model, and then generate on a finer grid. Or if I'm not happy with the quality, I could continue training. Some ideas that have been very popular in inverse problems and image processing that I think still are kind of not happening too much in diffusion models. So the first attempt really was to look at this for toy problems, because that's what GPU power we have. So you have some fashion MNIST images, you have different noise models in the columns, and then in the rows is, so the top row is sort of the resolution we trained the model on. These are 28 by 28 images. You look at these samples, you realize it's actually very hard to tell how good a generative model is, because you will just generate a bunch of images, and then it's your job to look at them and see if they look reasonable. Maybe they do here. They look like fashion items, most of them, with some exceptions. So let's say they are all trained on this level. And then the idea is, let's just use them and generate samples on a finer grid. So 56 by 56. And in this case, so far, we haven't been able to make it work. And here we had different noise models. So the noise, these ones here are all sort of well-posed priors that we're using, but we haven't touched the architecture. So we've used the standard UNet architecture that is, in some sense, you can think about it as an operator architecture, but it's not sort of set up in a continuous way. So when you change the resolution, you can still get score estimates, but there's nothing in the network that is invariant to resolution. So with Fourier neural operators, we were able to get a little bit more realistic images, especially for this is like a trace class operator built from just taking like an inverse Laplacian and taking some learned prior. We're actually able to see some light in the end of the tunnel, that these images look more reasonable. And again, the generator was not trained on 56 by 56 images. It has never seen them in the training. So we're really just training on the coarse and then seeing what can we do on the fine. In the paper, we have also examples what happens then if you continue the training, and turns out you can actually improve also. Okay, so there's that, and I'm at the time limit. So we'll not do optimal control today, but we'll summarize. So hopefully what I could show you is maybe some interesting, hopefully there was something new in this, hopefully, in terms of how you can build deep networks with continuous time. It's been a very popular area over the last couple of years, so you may have seen some of these things. But then I hope I could show you something about use cases in inverse problems, maybe relating to some of the work you're doing. And yeah, these are the main three references that we took a look at. You're happy to email me, or you're welcome to email me. We have time for questions now. And yeah, if you have any thoughts on so, I would appreciate that.
Great. Thanks so much for an excellent talk, Lars. So the floor is open for questions. So at this point, please, if you have questions, unmute yourself, and then you can ask Lars questions. Perhaps I could start with a question. So also, in ODS, you have discretization issues. So how does it translate to your problem here? Let's say choosing the number of layers and your configuration.
Yeah, that's an excellent question. I mean, I did not spend much time here in the talk, but we did spend a lot of time working on this. So generally speaking, you have two schools of thought, right? So you can either say you discretize your ODE and then you optimize the weights of this discrete object. So you need to choose a time integrator and you need to a priori choose the number of layers and where they are in time. Or you do it the other way around, which is sort of the optimized discretized, Euler-Lagrange equations, adjoint-based solution. And I think in inverse problems, people are in camp A or in camp B. Okay, the same thing now happens in machine learning too. I personally I'm happy in camp A, so I like to discretize and then optimize for a couple of reasons. One is simplicity. You actually get accurate gradients no matter how well I'm solving the ODE. And remember here, I'm not really forced to solve a given ODE because it's made up. It's not a physics problem where I have to kind of go there kind of really accurately. So we've done very well on this. The neural ODE, kind of, if you go right by the paper, actually interestingly does this optimized discretized approach, which I found quite remarkable because like for discretized optimized, everything is set up for you in machine learning frameworks because there's automatic differentiation. So you write your forward integrator and then you get gradients right there and then. But interestingly, that community has sort of put a lot of effort into implementing continuous in time like forward and adjoint solvers. And yeah, that has a benefit. You don't need to pick a time discretization a priori, but it has a downside that it's usually way slower. And also, I feel I have more control over discretized optimize because say I model my network as a Hamiltonian system, then I know which time integrator I want, and I can just use that. But yeah, there's much more to be said about it. There are actually a couple of papers also that are comparing these two paradigms. But it's a similar discussion that you have in inverse problems.
Any other questions for Lars?
Maybe I was too scary. I don't know.
Yeah, no, it was it's very, very nice actually. Could I ask one more question, perhaps? So, for the diffusion model, you sort of have the important thing. You have a drive-in Brownian field with a coefficient there, alpha t. So, what is important in terms of choosing this one?
That's a very good question. There are different rules about it. I think generally speaking, you need to make sure that you get to a Gaussian distribution in a finite time. So there's a cheat in some sense, because the diffusion models, when they are derived, they are talking about the asymptotic limit. But then in practice, of course, that's not what people do. So the noise scheduling is one of the crucial knobs people are tweaking here to make sure that the noise actually kind of becomes bigger in some sense, so that it's okay to stop at a good time. Can I give you new insights into that? I mean, like it's sort of to be honest, it's a very messy business still. I mean, it's better in the sense that prior diffusion models, I think the best image generation was GANs, so generative adversarial networks, and I think those really lack much of the insight and mathematics behind them. So for score-based, at least they're a little bit better, but it's still it's not a very clean problem by any stretch of the imagination. There's the stochasticity that's an issue. Of course, everything is non-linear in this case. You have a bunch of noise that comes in when you actually build the training objective, because you cannot observe the score, you can only have a conditional, and yeah, it's kind of it's been a really interesting thing to look into for us and to work on. But there's more to be done.
You may have touched upon this, but on this problem, when you sort of change the resolution, this sort of how does this affect the training?
Oh, so I mean, first of all, I mean, I should say this picture. Nicole, who's a postdoc here at Emory, she made this picture for me because I was sometimes what you still see is it's kind of the same dog in the top and the bottom. But I think it's very important to show different dogs. For sure, diversity and other things, but also, I mean, it's kind of really important that you're not trying to reverse a noise process on a given example, which would be hopeless, right? So yeah, so that's the one thing always to keep telling people that you're doing this on the distributional level. The nice thing here is sort of the forward problem is non-trainable, right? So you have a given process that is like a Fokker-Planck equation that asymptotically gets you to your Gaussian. So all the energy that goes in is actually to learn the score function that allows you the time reversal. There's a big shift compared to the previous parts of the talk in the sense that here, I mean, of course, this is also a continuous in time model, if you will, but the training does not involve time integration. When you build this objective function, so here's a simple version of the objective function, what you end up doing is you kind of randomly pick a time point. And so you pick an initial image x0, you randomly pick a time point, and that gives you sort of the appropriate noise level to add to that initial image, which gets you to xt. So you don't need to time integrate as you train, which is a big advantage for scalability, because you would not be able to train this with time integration. And sort of that is giving you when you randomize this over all of the noises and initial conditions, that gives you a way to estimate the score function to go back. And once you have that, you can go back to a continuous in time model. Actually, there's an underlying normalizing flow, like an ODE-based flow that has the same marginals. And sort of in some way, it's one technique how to learn these flows without time integration.
Great. Okay, well, thanks so much, Lars, for an excellent talk. Many interesting connections and challenges here. So I think you outlined them very well. So if there are any more questions, it's sort of the final round. But otherwise, let's thank Lars again for an excellent talk.
Sure, you're welcome.